we have, at this point, talked about the interference chapter entirely, which in Young and Friedman is 35. That's we're done. That's all of it. So now I'm about to move to the next chapter, whether that's Young and Friedman or OpenStax or whatever, about diffraction. So now's a great time to take a break. See you again at 8:15. Let me tell you before I mute myself that I'm going to pause the recording and then mute myself. All right. So we have discussed a little bit so far tonight about the extent to which the ray propagation model is not fully correct. But there are additional aspects to the propagation of light that the geometric model, the ray propagation model, does not account for. For example, sorry, I had a handful of chocolate-covered almonds on my way up the stairs, and it feels like there's like an almond fleck stuck in the back of my mouth. Hold on. So suppose we have a source of light and it passes near a straight-edged object, such that we expect, according to the ray propagation model, that there would be absolutely no illumination below this point. That is the ray of most downward propagation that we can draw that actually passes the straight edge. If I draw a ray with any downward incline, decline, it'll hit the straight edge and not propagate to the screen. So I expect there to be a sharp boundary, the very last ray I can draw, and above, a region of light and a region of shadow with a like sharp demarcation. That's not what happens. As an actual example, here is a picture on film. So here we have the film, the razor blade, and the illumination. And we're taking a photo on the film of what is produced by light behind the razor blade, sort of centered, I guess, on the razor blade. You can imagine the razor blade here. But notice these blurred edges. Notice, like, look closely. There's a region here of brightness around the edge, around the shadow created by the razor blade on the film. A region of brightness, and then actually a couple other thin sort of lines of brightness And there, there are actually lines that show up in the bright areas. I guess this is a razor blade with a sort of a manufactured um, opening in the middle, aperture of sorts. But there are these sort of blur markings all the way around. This is not two source interference. There aren't two sources. There's one source, a an obstruction, the material of the razor blade, and the screen. That's it. Where are these light and dark patterns coming from? Because these feel like interference. This pattern of light, alternating light and dark feels like the interference that we saw from a multiple source, a two source thing. This fringe pattern or banding that we could call it is as a result of diffraction. And we can wrap our minds around diffraction to some extent with an appeal to the Huygens principle, which said, remember, that if we consider a single wave front, that every point along that wave front can be thought of as a point source, each doing its circular propagation, ripples on the pond. And that if we collect the point, all the points, if we find the locus where all those, the next wave front for each of those sources seems to be, if our original wavefront was linear, just a straight line, think about a planar wave, each of those little circular propagations will have a wavefront a wavelength away from the original wavefront. And it'll just be another flat line, planar propagation as you're looking at it up. Which is fine, except that right at the edge, there's one more point source. Like we have a whole bunch of sources coming past the razor blade, but right at the edge of the razor blade, just next to it, there's one last Huygens point source. Which is doing spherical propagation. Which means some of the emanations from that last point source really close to the razor blade will, by the time they propagate the distance to the screen, have radiated into the shadow region, which is a cool sounding phrase. Sounds like something out of a comic book, you know. The Avengers, shadow region. I don't know. Anyway. It's been a long day. That propagation back into the shadow region blurs the edges of the shadow. So that helps explain why we don't get a sharp-edged shadow and illumination region. But if we have multiple point sources to consider around the boundary of this abstraction, there's some interference that could occur, resulting in an interference pattern. This fringing, possible because of diffraction, because of the spherical propagation of each sort of hypothetical point source along the wavefront, is actually the effect of the interference of those propagations from all the multiple sources. Again, this is the thing that doesn't happen. Ray optics does not, well, ray optics predicts this, cannot account for this. This is entirely a wave phenomena. And we can model it by considering Huygens sources at different points between the top and bottom of the slit. Suppose we consider a point source, a Huygens source, I'll say, right at the top of the slit, and one at the center line of the slit, the symmetry point of the slit. If we think about those two, they are like the two slits in the two slit interference pattern that we looked at a few slides ago, and can interfere with each other exactly the same way that those two sort of discretized sources that we talked about a few slides ago did then. Let's take a look. If we imagine little Huygens sources, little wavelets, and we talk about the wave fronts propagating from each of those little point sources spread throughout the slit. Close, here again, we have non-parallel rays such that the changing geometry makes this hard to describe analytically. We could do it computationally, but if we wanted an analytical solution, we should probably restrict ourselves to the far field such that all those rays are approximately parallel. We can cheat and use a lens to focus that point and end up with a Fraunhofer pattern, but that's, again, that needs a lens, and that's a little bit more work than I'd like to do at this point of the night. At this point in the semester, at this point. But figure C here, that's the sweet spot. Those parallel rays emanating from those individual Huygens sources will have path length differences, just like the path length differences of two slits. This top Huygens source and the next one down have path length differences. Imagine the little triangle right there. The top arrow is longer than the bottom by d sine theta, I guess, where d is the distance, but I'm getting myself confused now, where D is the distance between the two adjacent Huygens sources. But there's a whole mess of them. Like these are like thought instruments. They're not really individual points of light. They're a conceptual device. How close together are they? As close together as you imagined them, which is an impractical answer. Suppose instead we talked about the geometry of the slit width and the differences between the top and the middle. I don't have a picture. That's a shame. Trying to decide if I should try to draw one with a mouse on this PowerPoint. Wait, what else can I draw here? Arrow, pointer, highlighter. Nah, okay. That was a surprisingly straight line. It's almost like it knew what I wanted to do for a second there. Let's consider the Huygens ray that would propagate from the center line here. And that one which propagates from the bottom. These two paths, this is the maximum sort of, let's treat this as like a limiting case. From the center out, this is the largest possible path difference we can make. And it's related to, if we imagine this triangle here again, this side is half the width of the slit, A over 2. This angle here is the same as this angle here, so we can label the same angle. I can't draw theta, apparently. Close enough. That's a theta. Angle theta, there we go, is the same angle here. And the difference is related to A over 2 sine theta. And in this instance, I'm just going back to this picture. D sine theta the distance between those two rays that I drew A over 2 So the path difference is a over 2 sine theta. If the path difference between these two rays, that is one from the center and one from the edge to point P, and we're arguing that they're approximately parallel. It doesn't look like they're both hitting the same point, but if we put the screen far enough away that these two rays are essentially parallel, if the path difference is a over 2 sine theta, getting better at theta, if that were half integer wavelength, m plus half lambda, we would get destructive interference of these two rays. But consider the two Huygens sources, just one Huygens source up, one up from the bottom and one up from the center. Those two would also have a path difference that was half integer wavelength. And if you kicked up one more Huygens source, again, there would be a pair of Huygens sources with a path difference that was half integer. This angle theta would be associated all the way along the slit with destructive interference. In other words, the destructive spots are expressible in terms of integer wavelengths because we multiply both sides by 2. Find the common denominator for m plus half would be 2m plus 1 over 2 multiplied by 2, you've got 2m plus 1. So rejigger m, like call 2m some other integer, call it, I don't know, q, and then add 1. So q has the same 0 and 1 and 2, and then add 1, and now you're talking about all of the integers, but not 0. Which is good because if we put a 0, like what would be the 0? There can't be a destructive interference for path length difference 0. It needs to be non-zero. So m in this configuration can't be 0. It has to be integer wavelengths. Okay. This is a neat derivation. I think it's really, really quite cool. Instead of working through it algebra by algebra. I'm going to show you the broad strokes, and then actually I'm just going to pull up the text, and we can look at the algebra written out in the text and sort of annotate along verbally as we go. Okay, wait a minute. What the hell? Each Huygens wavelet has an amplitude, E0. Along the center line, the line from halfway through the slit to O, all of the different wavelets are in phase because every point along that line is equidistant between all the wavelets. Every point here is the same distance between pairs of wavelets, and so we get complete in phase, complete constructive interference. If we include a little bit of path difference, we include a little bit of phase difference. So each Huygens wavelet will have associated with it a slight extra phase shift relative to the previous one. The angle between one and the next, that's a consistent angle. All together, if we consider 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 of them, apparently. All together, the net phase difference between the original direction, just to the right, the original phase, and the final phase of the very last Huygens wavelet with the largest phase difference, because it also has the largest path difference. The overall phase difference is this angle beta. Now, beta has a lot to do with this triangle. Hold that thought. How many are there? Are there more than 14? Yeah, probably. They are as close together as you imagine them to be, which makes me think about calculus. They are as point source as you imagine, and that means there are as many of them between the opening of the slit as you want. Arbitrarily small and arbitrarily close together of arbitrary count. We're talking about the limit as these arrows become infinitesimally short, and what we have is a circular arc. I'm going to show you the result, which I can tell you what happened. I was going through the slides, preparing for class tonight, and I got to this slide and I said, where the hell did that come from? That's not great. That's crazy looking. Why does it look like that? And the next thing I did was open the textbook. So, all right, so let's take a look. Do I still have the textbook open somewhere? Yes. We are here talking about diffraction from a single slit. These are the diagrams that we've seen so far. Here's a better drawing than mine of the derivation of this condition, the dark fringe condition. But if we wanted to talk about the intensity, let's start here. This is the picture we were just working with. At the center line, all the little Huygens sources are in phase, and they just add up to the total electric field amplitude associated with the source. This is the picture we were just looking at. If we consider the limit where there are infinitely many sources, they become a circular arc of length E sub 0. If we express beta, the overall phase difference in radians, this becomes a circular sector of width beta. If we bisect it, beta over 2, these are radii, and if we think about the geometry of a circle and sector area and sector arc length, if this central angle is beta and this circular arc is E0, then the radii of that circular arc need to be in radians E0 over beta. All right, fine. That means that if we consider these right triangles, we're talking about E sub 0 over beta. Sine of beta over 2, E0 over beta. We're talking about the amplitude. This is like the phasor diagram. The amplitude of all these Huygens wavelets, we said, was the vector sum of all those little vectors, which is the, like, you can think of it almost like a secant line from A to B, which is just the sum where did this beta over 2 in the denominator come from? It's, if we divide by beta over 2, that 2 flops upstairs, and that's twice this expression. But we're writing it as sine thing over thing, which should make us think about limits and calculus and so on, because in a minute, if we keep scrolling through the text, we're going to see some cool sort of applications of limits to talk about where those minima occur. I thought this was a really neat geometrical but calculus inspired derivation for the actual electric field amplitude at point P. Then we know the intensity amplitude. The intensity at each point on the screen is proportional to the square of the amplitude. And so we get E sub 0 squared, which is I sub 0, and then the square of this expression. But the thing is, beta is expressible as the path difference, the same K times the path difference that we looked at before when we were talking about two slits. We wrote it as 2 pi over lambda K times R2 minus R1, but we wrote R2 minus R1 as A sine theta. All right, so if we replace beta in this expression with what we know that it's equal to from the geometry of the far field situation, we end up with this expression. I thought it was super cool. A really neat, like I said, a really neat geometry derivation with calculus baked in. It is super cool. And then we can do calculus with the result. Dark fringes are places where the intensity is 0. Sine theta is a geometrical thing having to do with the position of point P relative to the center line. That's not the 0 part. This is the 0 part. The sine of some stuff as theta changes. All right. If beta is a multiple of 2 pi, if beta is a multiple of 2 pi, then we're talking about the sine of pi, which is 0. So those are the zeros. So beta needs to be 2 pi, or in other words, a multiple. And we're back to the same result we had from geometry. What if we wanted to find the maxima? This is a worthy digression. This is not part of the slides, but it's worth talking about because there's going to be a slide later that claims that a particular thing is most effective, most accurate, if we consider high order, if we consider large angles. This is why. We might expect maxima when sine of stuff, sine of beta over 2 is 1. But there's the extra beta over 2 that modifies, because as we change beta, we're changing the denominator as well. So it affects where the maxima of this function actually live. This part is sort of scary. I can't highlight for some reason. There we go. If we try to optimize I, take the derivative with respect to beta and solve for the values of beta that make the thing maximum, we get a transcendental equation that cannot be solved analytically. So that's unnerving. The one that we expect near the neighborhood where beta is 3 pi actually occurs numerically. We can find it numeric with computational techniques at about 2.86 pi. So we're close. We're off by 0.14 out of 3 or so. 0.14 out of 2.8, I suppose. So what? That's 5%. The second maximum, the one that we expect near 5 pi, occurs at 4.918 pi. Again, this is all based on numerical calculations. But that's much closer agreement, and the agreement between our result and the actual pattern vanishes the further out we go. As theta increases, as the order of the maximum increases, our intuition about multiples of pi lines up better and better with the data. And so on. This I have slides for, so I'm going to hop back to the PowerPoint. The single slit diffraction pattern, which, should we call it a diffraction pattern? It's actually an interference pattern, but it's an interference pattern that results from diffraction. Potato. Depends on the relationship between the size of the slit and lambda, the wavelength. If the slit width is equal to or narrower than the wavelength, it's almost like, now sine theta, hold on, let me go back. The angle at which we get the first minimum in the single slit interference pattern, if A is smaller than the wavelength, M is going to be 1 or greater, which means lambda is bigger than A, which means this evaluates to more than 1. The sine of an angle can't be more than 1. And frankly, even if it evaluated to exactly 1, what, we need to have the screen, if the camera is the single slit and the screen is over here, the angle that we're talking about has to be 90 degrees, which, okay, if we draw the center line, how could we make, like, the screen has to be underneath my computer? There's no way for that to actually be real. So yeah, that makes perfect sense. If the slit width is the wavelength or smaller, a minimum is not mathematically possible. We will get some or other portion of a single maximum, and that's it. We won't have a minimum. We won't get a point where this intensity evaluates to 0. The larger the slit compared to the wavelength, the more we could argue that the ray model is correct. the wider the slit, the narrower and sharper is the central peak, the central maximum. So we could say that the ray propagation model is correct in the limit that the slit width is much larger than the wavelength. We do expect just a bright spot. Basically, with some fuzziness on the edges, no sharp edge between illumination and shadow. Let's return for a second to this scenario in which there are two slits, a distance d apart, for which the slits have finite width, finite size. There's two apertures of size A whose centers are a distance d apart. We have multiple things going on. We have the two slit interference, and we have individual aperture diffraction, related interference. The single slit diffraction pattern, there it is. The diffraction minima, m sub d, and the interference minima, or actually maxima, excuse me. Here's the fourth order maximum. Here's the eighth order maximum. But the total story is, as you might expect, something like the superposition of the two. If it is the case that the separation d is an integer number, multiple of the size of the slits, that means that at one particular spot in the double slit interference pattern, we will be sort of attenuated, enveloped by the zero, by the minimum in the single slit diffraction pattern. Here's the m equals 0, the center line, 1, 2, 3 maxima, and the fourth one is missing because that's where the minimum is in the single slit diffraction pattern. Then we get a small sort of local maximum, but even within that, you can see these 1, 2, 3, 1, 2, 3, double slit interference maxima. Back when we were talking about damped AC circuits, we said that the oscillation with respect to the inductor and the capacitor was modulated by the exponential decay dissipation through the resistor. Here we can think about the double slit cosine squared theta, this one, as being modulated by the single slit diffraction pattern. The same way the oscillation was modulated by the exponential decay in the AC circuit. Well, okay, what if we have multiple slits? The same argument applies. The path differences between, this is like the Huygens thing, kind of. If the path differences are integer wavelengths, now this is a picture with the lens put in so that we don't have to show the whole geometry, but basically the situation is the same as when we were talking about two-slit interference. We're talking about the interference of many slits. Just like the single slit pattern, though, we get better the more there are. The more slits there are, the sharper the pattern, which is kind of like saying the bigger the aperture, the sharper the pattern of the single slit pattern. That narrowing, we can see it a couple different ways, but one way to see it is from an energy conservation standpoint. If the intensity at each peak is proportional to the number of slits squared, in order to have the total energy proportional to the number of slits, because there are that many sources, so the total energy to work with is just a function of how many slits there are. Now, if the amplitude, if the height of each intensity maximum goes like n squared, then the total, the integrated intensity, I suppose, we need to make sure that it's proportional to n, because there are n slits, n sources. So each peak has to be sized 1 over n so that the proportionality goes like capital N. They have to get narrower if there are more of them. What if we have 1,000 of them? Okay, fine. We're talking about a diffraction grating, a grate, a whole mesh of apertures. Again, I kind of think this should be called an interference grating, but whatever, that's me. Especially as the number of apertures, the number of slits increases, the size of the slits contained in a given space has to decrease, which means we're getting closer and closer and closer to just individual source interference at the screen instead of like a finite size aperture. We're talking about the Huygens diffraction associated with the pattern that's produced. So for a diffraction, I really kind of want to call it an interference grating, but that's fine. It is what it is. It's hard to separate diffraction from interference once we get to this point. A similar phenomenon is responsible for the iridescent appearance of a DVD or a CD, this rainbowing effect. has to do with the grooves, the pits, which have a uniform radial spacing. And if that spacing is, if we can imagine that that's the spacing between slits, we've got an interference that's possible from the reflections associated with the differences in the path lengths from rays reflecting from the pits and rays reflecting from the surface. Otherwise, like, it's reflection instead of transmission, but otherwise it's exactly the same phenomenon. We can leverage this grating diffraction with a spectrograph. Here we have a diffraction grating. The angular orientation. Imagine that instead of a screen over here, we have this detector, step 6, that we can rotate around. Or I guess maybe we rotate the source instead. In any case, we're changing the angular orientation between the incoming direction and the measurement at point P on the screen. As we change the angle, we change the lambda that produces intensity maxima there. And we can use this to resolve multiple wavelength light into its constituents. We use the, you might have seen in chemistry when we talk about emission spectra and identifying hydrogen by the lines in its emission spectrum. Or mercury or sodium, or those lines are isolated. The individual wavelengths that make up the emissions from hydrogen as opposed to mercury or sodium or whatever are isolated by a spectrograph. We have multiple wavelengths, and of those wavelengths, each wavelength has a different theta at which interference maxima occur. And if we use a diffraction grating, those maxima are very narrow. So we sweep the angle until we find a bright, I don't know, red spot in the pattern. Okay, that means we're seeing the red wavelength at a particular angle. Because that's where its interference maximum occurs. If we examine the spectrum of sodium, for example, sodium has 2 lines in the yellow part of the visible spectrum that, if we don't look closely enough, actually just look like one line. resolving those two very similar yellow wavelengths means that we need to make sure we have enough resolving power, enough resolution. The minimum difference between wavelengths, the smallest difference between constituent wavelengths that can be distinguished by a spectrograph, is described by the chromatic resolving power. What wavelength can we see out of delta theta? Now, delta lambda is that minimum difference between wavelengths so that we can see that there is a difference. Notice that it depends on M. It depends on the order of the interference maximum that we're looking at, which I suspect has something to do with that little digression we made about the maxima in the interference pattern aligning better with our integer pi intuition as the order increases. All right, great. So if we want to get the smallest delta lambda possible, the best resolution, we should use the the largest possible number of slits and the largest possible order of diffraction, or I guess interference, whatever you want to call it. But we should also try to use the smallest wavelength we can get a hold of. To make delta lambda as small as possible. Now, I'm fudging the story a little bit here. The wavelengths we have in a spectral analysis sort of activated gas, spectral lines, that whole thing, emission spectra, that's what I'm looking for. The wavelengths we have are the wavelengths we have, but we can increase the resolution of some sort of electromagnetic measurement device. We can decrease delta lambda, we can increase the resolution. If we use smaller wavelengths to begin with. Let's get out of the visible range then, and let's talk about X-rays. Much higher frequency, past ultraviolet even, much smaller wavelength. With smaller wavelength light, we can probe smaller wavelength or smaller dimension phenomena. We can probe crystal structure of solids. This is a diagram of the setup for Lau diffraction. Which isn't the kind I'd like to spend most of our time talking about, well, most of the rest of our time. let's talk about diffraction. X-ray diffraction. By which I really mean interference. Again, we're sort of blurring appropriately, blurring the lines between diffraction and interference. Suppose we have an arrangement of atoms, scatterers, we could say. The plane waves incident. Now, this is electromagnetic waves incident on atoms, which are charged particles, essentially. The incoming electric field creates an oscillation at the atom. An oscillating atom, or electron, emits radiation. That's where we got the radiation from in the first place. With the same, generally, wavelength. Think of it like a sympathetic oscillation. But it's sort of like reflection. The incident plane waves coming down and to the right, and the emitted radiation by the scatterers is, you can think of it like a reflection. If the differences in the path length is the same, now, because these are atoms, right? There's a bajillion of them. So we want to make sure that the path difference for all of them is the same. Otherwise, they're all going to be different, and the whole thing's we're not going to get anything regular out of it. In order to make sure that we have like reliable, we should ensure that all the angles are the same, that we're talking about like a specular reflection sort of situation. This isn't two diagrams. This is all the same diagram. We've got incident plane waves coming in. These reflect, and so do these. These have path length differences associated with their propagation past the first row of scatterers to the next row of scatterers, and then back. Past the first row and then back to the first row. That's where this extra factor of 2 comes from. It's sort of like thin films and sort of like a diffraction grating. I'd like to say a little bit more about X-ray. I just keeping an eye on the time. About X-ray diffraction. And I'm going to give credit to Peter Muck at Portland State University, from whom I borrowed these slides from the internet. Notice that I have removed the Pearson copyright. These slides do not belong to Pearson. This is the same thing we just said. It's a little bit confusing, the relationship of this triangle to this diagram, but here's point A, point B, and point Z. So we're just looking at we're just trying to get at d sine theta. The distance AB is d sine theta, and there are two of those, the path length difference. Okay, great. So n lambda is related to 2d sine theta. That's that thing we just said. Great. What is HKL? This discussion about HKL is a little bit beyond the requirements for our course, for our understanding. I'm not going to test on this stuff, HKL, but it's worth a look because it's a practical application of diffraction from crystals by X-rays. We can measure the spacing between rows of atoms in a crystal structure. And we can determine the orientations of those spacings. We can measure the size, shape, and internal stress of small crystalline regions, which brings me all the way back to that introductory motivating question: how can I assess the stress or strain that a solid material was subjected to without cutting it in half to look at it? This way. The spacing between planes depends on which planes you're talking about. This plane, I suppose, of atoms up the face and across the back is a distance d2 away from the next horizontal plane. But vertically, these planes are stacked in the crystal structure as well. And this plane is a distance d1 away from the bottom of this cube of lattice. But that's not the only plane we could talk about. Suppose we talked about the diagonal from the front left corner or edge, I suppose, to the back right edge, and talked about a plane that cuts the cube, if rectangular prism, cuts it in half sort of diagonally. The next diagonal plane, because this is a lattice that exists in a larger crystal, so just a little bit out of the page, there's another atom right here that would be in a line, this dashed red line, along its diagonal sort of bisecting plane. And those two planes would be at a completely other distance apart. And there are other planes that we could consider. A, B, C, and the angles that we use to represent them are lattice parameters, which can be determined by the diffraction of X-rays from the crystal. HKL, here we go. A, B, C are actual lengths. Here we're measuring them in angstroms. From the bottom of the unit cell to point C, that's 3 angstroms. From the sort of origin to point A, that's 4 angstroms. To B, that's 8. If we consider a particular plane, the intercepts on those 3 axes of this particular plane are 1 angstrom, 4 angstroms, and 3 angstroms. compared to the actual length along those axes, that intercept length is 1/4 of the whole way to point A. This intercept length is half the distance from 0 to B, and this one is the full distance from 0 to C. HKL are what we call Miller indices, and they are the reciprocals of the intercept fractions. In order, A, B, C, the reciprocals of the fractions are 4, 2, 1. And so we can refer to this plane with its Miller indices. So the spacing between successive planes of orientation given by the Miller indices HKL and the angle associated, there's a particular angle at which there is constructive interference associated with diffraction from those planes of scatterers for the given wavelength. Here's some pictures. Just to point out the fact that you could consider multiple planes within the same unit cell. Here are some more. Okay, so how are we going to do this? We're going to create some X-rays by typically throwing electrons at a thing, causing the inner electrons to decay, emitting electromagnetic radiation energy, emitting electromagnetic radiation of X-ray wavelength. We send those X-rays at something that we're trying to image this way, and we're looking at the angle at which there are maxima, maximally detected intensity. Those angles and this wavelength of X-ray are associated with spacing between the planes of the crystal in this particular orientation of separation D. So we can use the diffraction angles that result when we use X-rays of wavelength lambda to tell us the spacing of a crystal orientation. How does that help? Again, we're tracking peaks in the detected, I guess technically it's reflection, but it's points at which the reflection has constructive interference associated with the fact that we're doing diffraction from multiple scatterers. For table salt, sodium chloride, the measured detector angle for diffraction from the 220 Miller plane, it's 46 degrees, which means the angle that we put into sine theta is half that. And we can walk backwards through the geometry to talk about the spacing for sodium chloride between the 220 planes. And if this is a cubic crystal structure, we can even use that to go back to the geometry of the cube and talk about the interatomic spacing, the size of the unit cell. So when we go to our textbook, and the textbook says that in a crystal of table salt, the sodium and the chlorine ions are this far apart. How do we know? This is how we know. Couldn't remember for a second whether it was chloride or chlorine that was the actual element. That's the peak we were just talking about. I'm particularly interested in this sort of long form digression about X-ray diffraction. If you're following along, at least in the Young and Friedman textbook, it's like 3 paragraphs. Nova has one of these. It's in CS on Annandale's campus. This is analysis that we could, in fact, perform. Here's an example. It's a little bit hard to read. This was a measurement made of the, notice, 2 theta, so that's the detector angles, and the measured intensity. And we see peaks in the intensity associated with interference maxima from the different planes of the crystal orientation. And here in this green notation, the system's giving us information about which planes are creating, because what we had to do is grind up the thing. And so there are many possible orientations. These are the crystal planar orientation, the Miller planes, I suppose, that are creating the different interference peaks that we're observing. Back when we used to teach on campus, which we're going back to, a lot of the classrooms in CS have chalkboards. So I needed to carry chalk with me. I got a box of ostensibly differently colored chalk from another professor. And this chalk, I don't know, I cannot describe to you the extent to which this chalk feels terrible to write with. It's powdery and flaky, and like it like when you write with it, it's like scraping your nail, like eroding your nail by operating it on the chalkboard, but it's like doing that with a piece of chalk, and that whole like vibration associated with that just propagates into your hand. It's terrible. It's terrible. Never mind the fact that they're all like, this one is supposed to be blue, I think, and it just kind of looks chalk colored. They're all kind of the same way. There are all kinds of different chalk you can get. Here's a box of Crayola chalk. What's the difference? Why does this feel better than that? So one of my previous students, I convinced, I suppose, I don't know. It was mostly his idea to examine different types of chalk to determine what the story was. Why are they different? So one of these pieces of terrible chalk was analyzed in NOVA's X-ray diffractometer. It's powderized, so that explains this whole mess of green planar information. The peaks in the interference pattern here, again, as a function of diffractometer angle, indicate that the composition, you got to squint a little bit, it's hard to read, is gypsum. Which, if I'm not mistaken, is at least partially responsible for the texture of drywall when you break it. That chalky, powdery, yeah, that's this. Not only can NOVA's X-ray diffractometer make this analysis, but based on the different geometries and the different wavelengths and the different, it can actually get you the crystal structure. Here's a calcium, here's the sulfur and 2 oxygens. Here, I think there are, I'm not sure where the other water is, but a sort of discrete full molecule, it might be hiding behind it, or it might be over here off the screen. Here's an H2O, and with another H2O, that's the calcium Ca H4O6S. That's the chemical formula and molecular configuration for gypsum. I don't know, it's, you take some stuff, look at this, I get dust all over my phone now. Stupid chalk. Take a thing, you don't know what it is, you mash it up, you put it in there, and poof. Not only do I know what it is, but I know its crystal structure. And I measure the distance, directly measure, well, I guess not with a ruler, but I can measure, I can ascertain the distances between these atoms. I couldn't do that except by leveraging the wave nature of light. We needed this chapter in order to make this analysis, in order to probe the interatomic structure of matter itself. We needed the wave behavior of light. I said something about this having to do with a non-destructive analysis of an engineering component. The width of the diffraction peaks has to do with the size of the particles and also relative to the standards. If we take steel and perform this analysis, the apparatus is a little bit different, but essentially it's the same. If we take your basic garden variety metal, the material out of which you would construct a weld, for example, and analyze that material, there would be diffraction peaks associated with its crystal structure, like everything else. If that material were subject to some strain, however, a uniform strain, in this case, we're talking tensile strain in the middle figure. We have stretched the sample so that D1 is slightly bigger than D0. The strain, which is the proportional length change as a result of tensile stress, ends up shifting the diffraction away from what we know, what the angle at which we know it should occur. If there is a non-uniform strain, if it isn't uniformly applied tensile strain across the crystal, if it has some curve to it, we can change the size of the diffraction peak. The top surface is subject to tensile stress. The bottom is subject to compressive stress, which means that whatever shift we would have gotten from the stretching of the top, I think, is canceled by the compression on the bottom. But that curvature, the differential spacing between the scatterers shifts the full width at half maximum, FWHM, of the diffraction peak. So we can use the diffraction pattern itself, the spectrum, from X-ray diffractometry of an existing substrate, I suppose, to determine whether and how much it has been subject to stresses without tearing the whole thing apart. It's almost time to be done. There's a couple more slides, a couple more things to say in this chapter. Circular apertures, not a linear slit, create interference patterns as well, or I suppose diffraction patterns. This discussion is relevant because the diffraction created by a circular aperture is the reason why our eyes can only resolve certain objects. If two objects are close enough together such that the angle is small in a visible wavelength for a given diameter, we can't actually tell the difference because of the diffraction associated with the circular aperture of our eye. And here's some other, those starburst patterns that you sometimes see in movies associated with headlights. This is what's going on. It's diffraction that means we need larger telescopes for better resolution. There are other uses for devices that measure interference. X-ray diffractometry is not the only way to do this. The Michelson interferometer has an important role to play in the history of science. For some time, it was thought that light, because we looked around at the other waves that we had experience with, we looked around and we said, every single wave we can find requires a medium in which to propagate. So we thought, so must light. There must be a medium in which light propagates. We called it the ether. And nothing else we did cared about the ether, but that there was this, it was like, it was made up. It was made up to fit the data before we knew what we were looking at. And it's like the force from Star Wars. It surrounds us. It pervades all space. And it's the thing that allows light to propagate. At least that's what we claimed at the time. The theory was that this was a medium that could flow, like water. It could, slosh. The Michelson interferometer was the experimental apparatus that was used to disprove the existence of the ether, which, now sounds like sort of a silly idea. If there was an ether that was flowing, it would result in a different speed of propagation, right? Because the light would be like a boat in a medium that was moving. So if light was traveling along the direction the ether was flowing, it would go faster. It would have an associated phase difference with respect to a propagation direction that was across the direction of the flow of the ether. So we designed a device to measure the interference between two paths. And this device was able to show that there was absolutely no difference between one path and the other path with respect to a hypothesized ether, and therefore there's no point making up the ether. It doesn't do any good for you. It doesn't mean anything. This same technique, actually, if you're following along, this is a bit of content back from the interference chapter, because it's an interferenceometer. But I put it at the end because it's very closely related to the process by which holograms are generated. In undergrad, I took an optics, a waves and optics class. It was, I don't know, I guess that was fourth or fifth year. I transferred, so I needed another year. And one of the labs we had to do in the course of this optics class was to create our own hologram. I still have mine. It's in a box on top of a shelf in my office on campus. The trouble is, it's constructed in the first place with coherent laser light of a particular wavelength, which means you can't see it unless you illuminate it with laser light of that same wavelength. And I haven't been able to get it, the orientation of the hologram film and the And the lasers we have on campus, I haven't been able to get it so that I could actually see the hologram again. I'm still trying, but if we were on campus, I would at least hold up a piece of glass and try to claim that there was a hologram inside. But the interference pattern stored in the film, when illuminated back the other way, manifests as the original image. Our eye is able to take the interference pattern as stored in the film and extrapolate to the image that was the photographic interferometric image of the object in the first place. Neat process, very cool. Sort of fun because you had to come in at night. So you like reserved time in the lab and you were the only one there working, and you turned off all the lights in the lab, and you got your little laser light. I don't know. And then you had to develop the film, and it was a whole thing. There was a dark room. It was great. Eventually I'm going to figure out how to illuminate the thing and see what the hologram is. But very, very cool. Has its own applications, by the way. It factored into the research I was doing in undergrad at the time. The chair of the department was using interferometric holography, like we just talked about, to image the vibrational nodes and antinodes of the material of brass instrument bells. When driven, it was a driven damped oscillator, driven at different frequencies. So trying to map the impedance, the acoustic impedance, that's a word we've seen before, of the physical oscillatory system using holography to map the like nodal, antinodal regions. Neat stuff. Like, this is all stuff that would not have been possible except for Maxwell. Except for Maxwell's symmetry hypothesis that a changing magnetic field also produces an electric field. Or that I can't remember which one it is now, that a changing electric field produces magnetic field, whichever one was missing. I guess it's the second one, right? Because we had to modify Ampere's law. Currents create magnetic fields, but also so do changing electric fields. That was Maxwell's addition. And that's the part where we got the wave equation from for electric fields propagating through. So it all comes back to Maxwell and the realization that what we were calling electromagnetic waves and what we were calling light are actually the same thing, because all of this stuff we just said only works if light is a wave. Thank you, everybody. Congratulations. You have made it to the end of a semester's worth of material. I will post exam prep tomorrow, and I will see you on Thursday. Thank you, everyone. Have a great night.